Okay, so guys, today what we're going to do is we're going to talk about electromagnetic spectra. And I'll just be honest with you, I love teaching this stuff. This stuff is really cool because all of a sudden, here, let me just switch slides. All of a sudden, guys, the work that Bohr did back in the 1920s, all of a sudden, guys, this stuff that seems all abstract and weird and Bohr is studying light and figuring out electron orbitals. Guys, all of a sudden, you're going to find out that this groundbreaking research that Bohr did almost 100 years ago is so accessible that in the next 20 minutes, I'm going to teach you the same stuff that got Bohr a PhD. It's really kind of cool how fundamentally just simple this stuff is, and yet realizing that Bohr didn't have the AP equation sheet and he was cooking this stuff up on his own. Clearly it was brilliant, and yet the logic behind it is eloquently simple. So guys, that's what we're going to do today. We are going to talk about what does it mean that Bohr studied light and how did he use light to figure out the electron structures for atoms. You ready to go? Okay, so guys, with that said, we've got to understand one fundamental thing. If you're in the lab, this will be somewhat familiar to you. If you're not, I think you've all seen this phenomenon, which are, where's my clicker thingy? Which are, come on, where's my picture? What is going on? This is not working. There we go. We'll come back to the previous slide. Guys, this idea, and you know what, let me switch these slides. This was supposed to have been before that, and it wasn't there. Guys, you're all familiar with this idea of spectra. You understand that if you take light and if you pass it through a prism, it spreads it out into a rainbow. We drew previously actually how rainbows happen. But guys, understand that when we talk about spectra, there are three fundamental types of spectra. First of all, we have what's called a continuous spectrum. And guys, this does us no good. There is no information contained in a continuous spectrum. You pass white light through a prism, you get all the colors of the rainbow. That has no practical value to us. The place where we get interested is in what are called emission spectra. And for those of you, again, that are in the lab, these are the spectra that you're studying in lab. If you don't understand this, fundamentally the idea, guys, and you understand this, remember from the flame test lab that we did last year? We took the Q-tips, we dipped it in the metal ion solutions, heated them up, and they created light. Well, guys, remember the connection that when you take an atom, when you take atoms, and when you add energy to them, remember the terms. When you add energy to an atom, the electrons jump outward into what we call, do you remember the term? An excited state. But guys, these excited states, these high energy states, are not favored. And as soon as the electron has the ability to fall, it will fall and re-radiate that energy in the form of light. And you may remember from last year that the color of light is an indication of how far that electron fell. So if you have an electron that's going through a long multi-energy level fall, that light will be on the violet end of the spectrum. And then conversely, if you've got a shorter fall, that will be redder light. Is that all ringing true with you? Okay, now guys, this is what you're going to learn to analyze today, which is fascinating stuff, because you're going to be able to figure out the electron structures of atoms simply by digging their emission spectra apart. Now, if you're curious, and this is worth mentioning, guys, we also have these things called absorption spectra. Less useful to us as chemists simply because we can control our laboratory environment. But guys, if you choose to get involved in astronomy, this is a big deal to you. Because while astronomers study hot balls of gas that we call stars, guys, astronomers are also very interested in cold balls of gas. They're called nebulae. And so what happens is astronomers can actually figure out what these nebulae are made of, even though they don't glow. And the way that they can do that is they can focus on a nebula out in space, and if they can line it up so that there's a source of light on the other side of the nebula, they can collect the light that goes through the nebula, and instead of seeing bright bands from the emission, you actually see dark bands as the electrons and the atoms in the cold gas are being excited. Does that make sense? Now, guys, here's the thing that's interesting. And I don't know if this is true, but imagine that this is the emission spectra for hydrogen. Let's just say that it is. Well, it turns out that if this cold gas is a big ball of hydrogen, when you shine white light through it, what you will see is the inverse. Is that a good word? You see what I'm saying? So this represents an electron going through a short fall. Well, guys, this represents that same electron going through a short rise, because the idea is this white light contains all wavelengths of energy, and this wavelength of energy is absorbed as that electron rises, and then we know that it can then be re-radiated as the electron falls. Does that make sense? But you see where this gets really nasty, right? Guys, what if the light that was passing through that cloud was not white light? What if the light that was passing through the cloud was actually an emission spectra from another element? Yeah, then you've got missing lines and you've got redshift, and you don't know what your distance source is, so you don't know what lines you should be seeing, and you also don't know what lines are missing because of the absorption of the interfering gas, and everything's shifted to the right, and all of a sudden you're really glad for computers that can look at that spectra and not only figure out what's being absorbed, but also what the substance is on the other side that's doing the initial radiation. It's fascinating stuff. One of the things that you get to learn more about if you do astronomy. Okay, so guys, you okay with these ideas of spectra? And understand again, this is the one that has meaning to us, because we get to control our environment. We don't put cold gases between us and our sample gas, and as a result, it's emission spectra that we look at. Yeah. Great question. So the question on the table, guys, is it just the valence electrons that jump? And the answer is absolutely not. All of these electrons are excitable. Okay? But guys, please hear this as well, because this could be confusing to you. Oh gosh, is now a good time to mention this? It may not be, but I'm just going to lay it out there, and then if you don't have context for it, we'll talk about it in a minute. So your question is good. Is it just the valence electrons that excite? And the answer is no. But similarly, maybe the best way to do that is this. Let's try this, because this could be, this will confuse you in the homework. So let me just mention it now. So guys, we've got one proton, so that's hydrogen, right? Hydrogen has got one electron, and what sublevel is that electron in? 1s, right? Remember that? That electron is in a 1s sublevel, but you are going to see stuff in the homework that talks about an electron in hydrogen in the third energy level. And you're going, wait a second, hydrogen doesn't have a third energy level. Hydrogen's got a 1s and that's it. It doesn't have a 2s or a 2p. It certainly doesn't have a third energy level. And guys, here's the thing you've got to understand. When these electrons excite, they can excite into energy levels that the atom itself doesn't have until that electron excites. So you're going to see stuff in homework that talks about the 2s sublevel of hydrogen. And you're like, wait a minute, hydrogen doesn't have a 2s. Well, it does if you excite that electron into the 2s. Okay, so understand that when these electrons excite, they create, if you will, sublevels and energy levels that don't exist until that excitation takes place. Does that make sense? Okay, yeah. So it leaves a vacancy. Yes, yep, that's true. Understand, with hydrogen, there's only one electron there, so you could think of it as if that energy level no longer exists, but the probability of it existing is still present. Because remember, these energy levels are not like streets in a neighborhood. They are merely probabilities. And there's a high probability that you'll find an electron here. There's a high probability you'll find an electron here. There's zero probability that you'll find an electron in between. And that's why we see these rungs, just a second, that's why we see the rungs on the ladder rather than the ramp, because there are places where electrons can be and places where they won't be. But understand that those are really probabilities. Yeah, go ahead, Brian. Can we say the electrons in any atom?
The electrons in any atom.
Yes.
So if we can go beyond our max of periodicity.
Oh, absolutely. Yeah, and
electron.
absolutely. And in just a second, we're actually going to talk about orbital infinity, energy level infinity. Yeah. So we understand that for the elements that we have in our world, we only go up to 7p, right? So 7p is the highest occupied orbital sublevel in our reality. But understand, there is an 8th and a 9th and a 10th and an 11th and a 12th potential energy level that we can promote into. The electrons can be promoted into. Just a second. Go ahead, Anna.
So if we can go into the next energy level, like, why are we distinctly what makes it go into specific ones and specific drugs? Why do
Right, it does. And so could I where's my book? Could I paraphrase your question as saying, why are there places where these electrons can be and why are there places where they can't be?
Well, I understand they can't be like in between.
Yes. Yes.
Just like, could that electron jump into anything it wanted to? Could it jump into any orbital?
Good. Let me take a swing at this, and if I'm not understanding your question, phrase it again. But let's do this. Let's say that we've got an electron right here, and then allow me to draw in some more energy levels, and we understand they're not spheres. That's your mess, huh? Yeah. I know. But you understand that it's messy. It's not really spheres. It's 1s, 2s, 2p, right? But we're just going to draw circles. So here's the deal. This electron can be here, this electron can be here, it can be here, and it can be here, but it can't be in between. So how do we know what is it that determines where it's going to go? And the answer is the amount of energy that is available to it to get excited. So if it takes 10 joules of energy, I'm just making up numbers, but if it takes 10 joules of energy to make that jump take place, and if we hit this electron with 8 joules of energy, what will happen? Nothing. It doesn't have enough energy to get there. What if we hit it with 11 joules of energy? What will happen? Still nothing. It can only absorb exactly enough energy to make this jump. If we add more or less, it will not move, unless we add enough energy that the electron completely gets kicked out of the atom, and that's what question number 31 was about in the homework. Did that answer your question? So, yes or sort of? Okay, so if it's not, let me know. Tell me just a second, because Jake beat you. Go ahead.
So this, there are, like you're saying, there's like infinitely many energy levels. So theoretically, since the probability is never asymptotically approaches zero, never gets there.
That's true.
So you have the nucleus, you have a proton on one side of the universe, and its electron on the opposite side.
Yeah, but
Still,
but understand, well, we're going to talk about that because I know that asymptotes create great opportunity to get vague, right? Because it never, like half-life, it never fully goes away. It's an asymptote. Okay, but so yes, but in practicality, what we're going to find out is there is this moment, we're going to call it energy level infinity, but there is this moment at which that electron, for all practical purposes, is no longer attached to that nucleus, creating ions. And we're going to deal with, you're right that that's an asymptote, but we're still going to treat it as if there's a removal. Does that make sense? Go ahead, Talmadge. Correct. Yes, yes, and that's important. That, guys, this electron, if it's hit with 11 joules, can't grab 10 and just sort of pass the 1 extra joule off to a friend, unless it's enough energy to get that electron all the way out to here where we hit that point of escape. And then it will take that energy, that extra energy with it in the form of acceleration. But if it's not enough energy to allow that electron to escape, it just won't jump. Does that make sense? Okay, go ahead. Right, and so we're going to calculate that. We're going to be able to answer, today we're going to be able to answer the question, how much energy does it take to get it to escape? Can I use that as a, you know what, you brought it up, let's talk about it. Guys, you already know the answer to that question. How much energy does it cost, let me say it different, how much energy is required to strip an electron from an atom? How much energy is required to strip an electron from an atom? You already know the name of this number. It's called ionization energy. Do you guys remember last year we talked about periodic trends? We said as you move across a period, the atomic number goes up, the atomic mass goes up, the atomic radius goes down. Do you remember that? We drew the arrows. And then we talked about electronegativity. And we said, as you go left to right, the electronegativity goes up because the atoms are getting smaller and stronger. And then the last trend that we talked about was ionization energy. And we defined ionization energy as the amount of energy required to strip an electron from an atom. We said that the trend followed electronegativity, and we went over it very briefly. But guys, that's what ionization energy is that amount of energy necessary to strip an electron from an atom. Now what we're going to talk about today is so ionization energy is actually the amount of energy required to promote an electron to energy level infinity. And you're going to do that math today in homework, and you're going to calculate the amount of energy needed to promote an electron into energy level infinity, and then you're going to compare it to the ionization energy on the periodic table for that element, and you're going to find out they're the same. It's kind of an interesting question. Okay, so why on earth are we talking about this? I have no idea. Oh, we were talking about spectra. So guys, are you okay with this idea of spectra and that there are places where these electrons can and can't be? When the electron promotes to an excited state and then falls down, it releases light. The longer the fall, the more violet the light. You guys good with that? Okay. Now guys, in order to tie this all back together, the connecting thought that we need to make sure we're clear on is this. So this is the lot, oh golly, wow. I think my computer needs to restart. It's got a lot on its mind. Okay, so guys, you may want to write this down because this is the big connecting thought. So you ready? It goes like this. Falling electrons lead to colors of light. These colors of light are a direct reflection of wavelength. These wavelengths can then be converted into frequencies, and these frequencies can then be converted into energies. And if you don't remember the equations, we've got C is equal to lambda nu, and E is equal to H nu. So guys, this is the logical progression of thought that we are going to leverage today. And this is the trick behind spectra. Falling electrons release light. We can tell how far those electrons fell by the color of light. But color is a function of wavelength, which is also a function of frequency. And if we know the frequency, we can figure out the energy. You see those related concepts? Well, it's here. So the idea is falling electrons release light. We know qualitatively, we know the length of the fall by the color of light. The longer the fall, the more violet the light. The shorter the fall, the more red the light. But color of light is actually a function of wavelength, which is a related function to frequency. But frequencies we can convert into energies. Does that logic make sense? That's sort of, I mean, if you think about it this way, you might say this. This was last year, right? Last year, during this unit, when we did the flame test lab, we said that color is a function of how long the fall is. This is functionally this year, where we have said that color is related to wavelength, frequency, and energy, and we can make all of those connections given these two equations. You okay with that? Okay, so now guys, here's what we're going to do today. We are going to move in the other direction. We are going to figure out when an electron goes from here to here, when an electron goes from here to here, how much energy will that release? It's a really simple calculation. As soon as we know how much energy that electron will release, we can figure out its frequency, and we can figure out its wavelength, and we can then relate that to the colors that we see in a spectra. You get the idea? Okay. So guys, the question then is, how do we make that backwards connection? So fundamentally, the question is, how do we know how much energy will be released when an electron goes through any particular fall? And that's the question we're going to answer right now. You ready to go? Okay, so let me clean up my mess, and this, and this, and we can now skip over the types of spectra because we just talked about it. And here we go. Yes. Okay. So guys, this then becomes the idea. And I would encourage you to not write this down, because this is basically a verbal summary of what we just said. But guys, the logic goes like this. We understand that the bands of color in an emission spectra corresponds to the energies that are being released when electrons fall. You good with that idea? Okay, so to relate these spectra to electron structure, remember this is what Bohr did, right? He made these connections between the spectra and electron structure. Guys, what we've got to do is we've got to quantify how much energy does each energy level have. Do you see the connection? Remember our question is, if an electron goes from here to here, how much energy will that release? Well, guys, in order to figure that out, what we need to know is how much energy does an electron have here? How much energy does an electron have here? And if we know these two energies, when it falls, it will release the difference in those energies. Okay, so in order to do that, we need to know the energy of the energy levels. Now, guys, here's the beautiful thing. The equation that you need to know to figure out the energies of these energy levels is simple, stupid, easy. Understand that Bohr is the one that came up with this equation. And when he did, it wasn't that obvious. The science behind how he came up with this is amazing. But now that he's come up with it, the equation is beautifully simple. And it goes like this. Write it down with me. Guys, this is the equation. It's too small, isn't it? Guys, this is the equation. E, which is the energy of an energy level, is equal to negative R sub h divided by n squared. So guys, what does n represent, remembering from last year? The number of the energy level. On our periodic table, that ranges from 1 to 7. So notice what we're learning. We're learning that the energy of an energy level decreases by the square of the energy level. It's not a linear relationship. But let's make sure we're clear. N is the principal quantum number. And guys, you're going to find out in a minute, R sub h is what is called the Rydberg constant. And guys, the Rydberg constant has a value of 100 joules. Yeah. Okay, you ready? So here's what we're going to do. We are now going to take this equation, and you're about to find out why this is in such a weird place on the screen. We're going to take this equation, and we are going to apply it to an atom. And so, guys, we are only going to represent the first 5 energy levels in an atom, and we are going to figure this out. This is going to be our big question. When we have an electron that promotes to energy level 4 and then falls to energy level 1, how much energy will that electron radiate? Now, in order to know that answer, what do we need to know? The energies of the energy levels. Now, guys, in order to figure that out, what we need is the Rydberg constant and this simple equation. So, guys, this is the way this goes. How much energy does energy level 1 have? Well, guys, plug 1 in for N and plug 100 in for R sub h. So you have negative 100 divided by 1 squared, which is what? Negative 100. So guys, I'm going to just roll. So the energy of energy level 1 is negative 100 joules. Let's keep doing the math. Guys, what is the energy of energy level number 2? Negative 25 joules. Does that make sense? So it's negative 100 divided by 2 squared, which is 4. 100 divided by 4 is 25. What is the energy then of energy level 3? Well, it's negative 100 divided by 9. We're going to call that 10 joules. We're rounding. Maybe 11 would be better, but really 11's better, huh? I will make it 11. I rounded carelessly. All right, hold on. Let me make it 11. All right. So here we go. And, oh, there's our, and we've got bump, bump, bump. Okay. Now, guys, energy level 4. Energy level 4 would be negative 100 divided by 4 squared, which is 16. I'm going to call that close enough to 6. And then, guys, finally, energy level 5, negative 100 divided by 25, and that would be negative 4. You good with the math? Now, guys, let's have this conversation. What on stinking earth do these numbers mean? So guys, let's talk about it. What do these numbers mean? So what does it mean that an electron in energy level 1 has an energy of 100 joules? But understand that that electron in energy level 1 does not have an energy of 100 joules. It has an energy of negative 100 joules. That's like saying something weighs negative 100 pounds. So guys, let's talk about the negative sign first, and let's get rid of that issue. How on stinking earth can you have an energy of negative energy? Negative 1, negative whatever, all these numbers are negative. How can it be that you can have an energy that is negative? We know that you can't have negative mass. You can't have negative height. You can't be -5 feet tall. It'd be kind of fun to picture. Guys, how can you have negative energy? Go ahead.
Because when they fall, they're releasing energy.
Sure, but that could still be the same. This could be 120, and they could still. You're right that when they fall, they release energy, and that doesn't refute this, but it doesn't explain it. It's got to be entropy, right? It's like in Sunday school, the answer is always Jesus, regardless of the question, right? It's got to be, or better yet, Gibbs free energy. No, it's not because of entropy. So, guys, why? What explains a negative energy? Guys, the answer is because it's an energy of association. Here's the deal. Think about it this way. What is it that gives this electron energy in the first place? It's not, then this, good point. This has nothing to do with charge. This is not an electron has a charge of -100. This is completely independent of charge. This is energy. Say it again. Guys, do you get that? That the only thing that gives this electron energy is position. Position relative to what? The nucleus. Now, guys, with that underlying understanding, think about it this way. In order to move the electron away from the nucleus, what do we have to do? We have to give it energy, right? We've got to add energy to that electron to get it to promote. Stick with me, Rebecca. So we've got to add energy to get that electron to promote. But guys, come back to that underlying idea that the only reason that electron has energy in the first place is because of its position relative to the nucleus. Now, guys, give me a hand down, give me a fist. There's our nucleus, okay? So this electron has got energy because its position relative to the nucleus. Now, guys, if we can add enough energy to that electron, if we can get that electron all the way over here, we are going to say that that electron is no longer associated with the nucleus. And if we've broken that association, we have removed, that electron no longer has the ability to have energy because its ability to have energy is completely dependent upon its relationship to the nucleus. And if we can break that relationship, what is now the energy of this electron? 0. But guys, think about it this way. What do we have to do to get that electron far enough away that its energy becomes 0? We have to add energy. And if the addition of energy is always positive, the energy of association we have to think of as being negative, so that adding energy increases the energy of the electron to a maximum of 0. That's, just a second, that's why it's negative. Because, guys, understand that this negative sign is just an arbitrary directional thought. But the reason that it has to be negative is because the most energy an electron can have is none. Think about that. The most energy an electron can have is none. Because when this electron has no energy, it's no longer associated with the nucleus. So if the most energy an electron can have is none, as that electron is getting less and less energy relative to a maximum of 0, that energy's got to be negative. Does that make sense? So guys, the bottom line is the negative signs on these energies are simply a reflection of the positional source of that energy, which is relative to the nucleus up to a maximum of 0, where there is no association. Does that make sense? Go ahead.
What about photoelectron spectrum?
Let's not talk about, we won't go there today. No, go ahead.
So all of those energy levels is dependent on the electron being tied to these nucleus.
Correct.
And electrons they aren't always attached to nuclei.
But if you have an electron that is not attached to a nuclei, a free roaming electron, that electron does not possess this energy. Yeah, and here's why. What kind of energy is this? Potential or kinetic? Potential energy, right? If that electron is removed from the nucleus, the only energy, it has no potential energy. But it could have kinetic energy because of its velocity. And Jake, I'm sorry I sat on you. But that's all about PES. That's the whole idea behind PES that we'll get to later. Go ahead.
So those numbers are the same no matter what element it is?
No. And so guys, let's do this really quickly. This equation only works for hydrogen. When you get into multi-electron atoms, the Rydberg constant changes. And so and the equation becomes much more complicated. You end up with multiple variables that describe the interference, the shielding from other electrons. So this only works for hydrogen. Go ahead.
So you're saying it takes 75 joules to get from the first level?
Good. Okay, guys, now let's do this. You ready? Let's do Matt's question first. So guys, we've got an electron in energy level 1. How much energy does it take to promote it to energy level 2? 75 joules. Get the idea? To get that electron from there to there is 75 joules. But now let's do this. Let's answer our initial question. If you've got an electron in energy level 4, and if it falls down to energy level 1, how much energy does it radiate? And guys, the equation, and I know you can probably look at this and do the math, but guys, just trust me on this. You're going to get so lost in the midst of all of this. You want an equation to come back to, and it's a familiar equation. You may want to write this down with me. Changes are always final minus initial. So the change in energy is the energy final, which is negative 100 joules, minus your initial energy, which is negative 6 joules. So what is the change in energy? Negative 94 joules. Now guys, let's talk about what that means. The 94 is obviously the amount of energy that is radiated in the form of light. What does it mean that this number is negative? The energy is being released, and we would suspect that because the electron is falling. You get the idea? So guys, that's how to approach, and this was the brilliance of what Bohr did. He figured out this equation, obviously with the help of a guy named Rydberg, who doesn't get a lot of credit when we teach this to general chemistry people. Rydberg is actually the one working with Bohr that helped him associate the energies of the energy levels. But guys, through this simple final minus initial math, you can figure out the energy of these photons. But now, guys, this is where this gets interesting, because now we can do what I wrote in blue on the white screen. Now that we know the energy, we can take that energy and convert it into a frequency. When we know the frequency, we know the wavelength. When we know the wavelength, we know the color, and we can take that all the way backwards to the energy level changes that they represent. With one little problem, and only Matt figured this out. Guys, these numbers are huge. The reason that they're huge is because the Rydberg constant is actually not 100 joules. I use the number 100 because if I showed you the actual value for the Rydberg constant, your brains would have got so focused on that number that you wouldn't have been able to figure out the math. So guys, understand the Rydberg constant is not 100, but the logic all holds true. So what is the Rydberg constant? Well guys, the Rydberg constant is actually 2.18 times 10 to the negative 18th. Well, realize what I was doing was saving you from yourselves. So guys, what then can we do with this practically? Well guys, the practical side of this then becomes, well, maybe before we get practical, let's make sure you guys are good on this idea. We understand that n is the principal quantum number. Are you okay with the idea that as a result, all of these energy values are negative to a maximum of 0? And all of that is true because of our frame of reference. 0 energy means 0 association. And if our maximum at the greatest radii, if you will, if our maximum is 0, relative to that, everything's got to be negative. But guys, with that true then, we know this. We know that as n goes up, the radius increases. We know that the energy increases, but again, it increases by becoming less negative. Negative 100, negative 25, negative 11, whatever it was. You remember the progression. But guys, the energies do increase. They increase by becoming more negative. And again, guys, what happens when n goes to infinity? Energy goes to 0. And that's the point at which we say the electron is no longer associated with the nucleus, and that is the same as ionization energy. Do you buy it? You picking up what I'm laying down? So guys, you all caught up? Yeah.
And the electrons will never crash.
No. No. No.
And that's just law of nature.
No, it's so, and that was, this has nothing to do with what we're doing, but we'll talk about it really quickly. That was one of the things that led Schrodinger to think that this whole Bohr model was at some level fundamentally broken. Because as electrons move through space, they radiate energy. As they rise and fall, they radiate energy, we can see, but as they move through space, they radiate energy. Anything moving through space radiates energy. If something's always losing energy, it should also be slowing down. And if that's the case, eventually it should spiral into the nucleus. And because we know electrons don't spiral into the nucleus, we knew that there had to be something fundamentally flawed about Bohr's model of the atom. It turns out that the explanation to that was Schrodinger's idea that electrons fundamentally are not particles, they're waves. And if we treat them as waves, then the radii at which those waves become self-reinforcing, remember we drew that on, yeah, the radii at which those things become self-reinforcing, they're actually, if you will, re-energizing themselves. They're reinforcing themselves, and it's what allows them to stay indefinitely in those orbits. We're going to leave it at that for now. Okay, so guys, here's what we're going to do now. By pulling all of this stuff together, we can now answer this question. It says this. It says, calculate the wavelength of light that corresponds to the transition of an electron. You know what? Hold on. I should add something to this. Calculate the wavelength of light that corresponds to the transition of the electron, the hydrogen electron, moving from the fourth to the second energy level. So if you've got an electron in hydrogen going from energy level 4 to energy level 2, what wavelength of light will that electron radiate? So guys, in order to figure this out, what's the first thing we need to know? The energy of those energy levels. So we're going to go like this. We're going to go E is equal to negative R sub H divided by n squared. Now, the Rydberg constant, what is it, 2.1 what? 18 times 10 to the what? Are they both 18s? 2.18 times 10 to the negative 18th joules. And for energy level 2, well, 4, this will be 4 squared. And then similarly, negative 2.18 times 10 to the negative 18th joules, and then divided by 2 squared, will give us the energy of energy level 2. So we go 2.18 times 10 to the 18, negative 2. And then that will be divided by 16. So guys, here I get negative, and please check my math, 1.36 times 10 to the negative 17th joules. Wow. No? I trust you more than me because I was talking as I was typing. So 2.18 times 10 to the negative 18th, divide that by 16. I did 2. So you guys probably already have this number too. What is it? 5 point what? 45 times 10 to the negative 19th. Okay, and both of these are joules. So then, to figure out the energy of this photon as it goes from one to the other, we're simply going to say change in energy is equal to energy final minus energy initial. Our final energy, and is it going from 4 to 2 or 2 to 4? 4 to 2, so our final energy is negative 5.45 times 10 to the negative 19th minus a negative 1.36 times 10 to the negative 19th joules. Does anyone have that yet? 4.0 times 10 to the negative 19th, and we know that's wrong. Right, so negative, not well negative. Without the negative, it's wrong. Because the change in energy is negative, telling us what? The electron's falling. But that is simply just reinforcing our idea that it's going from 4 to 2. The energy has to be radiated. Now, guys, we've got the energy. How do we come up with wavelength? So E is equal to h nu. So negative 4.09 times 10 to the negative 19th is equal to, what's h? 6.63 times 10 to the negative 34th times x. So x is equal to 4.09 times 10 to the negative 19th divided by 6.63 times 10 to the negative 34th. And I get 6.17 times 10 to the 14th hertz. Now, guys, what about the negative in that calculation? You can drop it. The negative is simply telling you that that energy is radiated. But when you start solving for frequency, we've already established that it's radiated. And a negative frequency still just tells us direction, but at that point you can drop it. And then, guys, of course, the final calculation, and I'm hurting for space, but I'll put it on this page. C is equal to lambda nu, or 3, I'm going to get really crazy with significant digits, is equal to x times 6.17 times 10 to the 14th. So we have 3 times 10 to the 8th divided by 6.17 times 10 to the 14th. And I get 486 nanometers. It's actually 4.86 times 10 to the negative 7th, but that's equivalent to 486 nanometers. You could, let me show you why I put it in nanometers. Meters is fine. Unless, and guys, be careful on the test. Many times it will specify nanometers, but understand the answer is 486 nanometers, right? Well, guys, check this out. If we go back here, oops. If we go back here, 486 nanometers, blue light. So guys, when an electron falls from energy level 4 to energy level 2, that light will be blue. Right, in a hydrogen atom. Understand that for multi-electron atoms, it's similar, but not exactly the same. All right, so guys, with all of that said, let's do some of this.